G'day everybody, hope everyone's well. So first things first, I hope everyone had a very Merry Christmas and a Happy New Year. There's currently still work being done. The Patrol seems to be running alright with the new turbo. There's still a bit of R&D I've got to do, a few more things. I'll have a video coming out about the BMW in the near future. So, as I'm sure all of you know, my upload frequency is lacking. So the reason for this is that I've believed that the format that works the best for this channel is information density. You see all of the videos where I'm talking through the mic and there's sort of animations going on screen. They've all seemed to be the best and the highest regard videos in my channel. And so I'm going to keep that going. The only problem with running like this is the upload frequency has to lack because I need to get X amount of work done before I have enough content or I have enough work done to deem an entire video worth of information. I don't mind this. This is fine for me to work with. I enjoy making the format like this as I believe that keeps viewers engaged because it's not just me taking bolts out for 20 minutes and talking about random shit. It's me actually physically getting something done and people learning things quickly. I do feel that I need more upload frequency. I need to stay engaged a bit more. Again, it's hard to do that with the format that I run with. And so because of that, and due to 1,500 subscribers, I've decided that I'm going to launch a new chain of videos. So this video series is going to be called Back to Basics. In this series we're going to dive into the fundamental parts of mechanic work to hopefully teach people a thing or two they didn't know already. A lot of these things I will have explained in previous videos, way back when, like 2 years ago when I uploaded 40-minute videos of me just talking straight into the camera. Those videos aren't properly engaging enough. You've got to watch 40 minutes of pretty much nothing to learn a little bit. What I'm going to do is I'm going to compile all this information of various topics about mechanic work into singular videos. These will be sort of various things that it's good to have a full understanding of. Things such as bolt torques, things such as turbo sizing, things such as pressure. Pretty much simple things that you don't necessarily need to know a whole lot about, however it's good to know. So kicking off this new series, I've selected a topic and we're going to delve into wiring and relays. We're pretty much going to cover wiring and relays in as much in-depth detail as I can, so that if you watch this entire video you're going to come out with an understanding where you'll feel comfortable doing your own wiring on your car. So, enough talking, let's get into this. So, probably the most important component of any modern vehicle, next to an internal combustion engine or a stinky electric motor, is wires and relays. These carry everything from power to fuel pump to CAN bus wires on board, allowing diagnostics and things. To brief everyone up to speed, cars mostly operate with DC or direct current voltages. AC is used in certain areas, but we won't worry about that right now. So DC current can only travel one way, positive to negative. We won't dive into the batteries and all of that right now, that's a down the track thing. This is because batteries will induce electron flow from the negative terminal to the positive, which sounds stupid, but that's just how it is. And I'm not going to confuse anyone, we'll just focus on the wires now, which run positive to negative of the battery. The easy thing about cars with their wiring is that the DC voltage is conveyed through the entire body of the car. This means everything metal on the car is earthed or connected to the negative terminal of the battery. This is done so that every electrical component has a really solid earth and there's less chance of things going wrong with bad earths. So now that we know about the foundation of the system, we can start talking about wires. So let's talk through a few examples. The first example is a fuel pump. A fuel pump requires power to turn on and supply fuel pressure to the fuel rail or the injector pump. Most stock cars will use a small fuel pump, usually around 130 or 160 litres per hour of flow. These pumps will in turn have a much lower current draw than a high flow racing pump. These ones will supply all the way upwards of 500 litres per hour. I'll give you an example of where you need to know wiring and how to do it properly. When I swapped from the stock fuel pump to the upgraded Walbro pump in my Hilux, I had issues with the Walbro fuel pump supplying enough fuel pressure. So the reason for this is the stock fuel pump in the Hilux, its 12 volt current is supplied from the same bus wire that supplies the idle speed control valve, the MAF sensor and various other 12 volt apparatuses in the car. All of these ran through a 15 amp fuse in the engine bay. When you upgrade a fuel pump, this is usually standard that you will put your own fuel pump relay in. The reason for this is the newer fuel pump, in the worst case scenario, it draws too much current and it'll pop the fuse and your car won't run, or it will pull just enough current to where the fuse remains intact, but there's enough of a voltage drop across the wire where you'll have problems with the fuel pump not supplying enough fuel, or you'll have other problems with the 12 volt apparatuses in your car. Fuses are a safety feature. If you pull too much current through the wire, instead of the wire heating up and burning, the fuse just pops so that you can replace it and make changes so that it doesn't happen again. So when we installed the big beefy fuel pump in the Hilux, we installed our own relay. This relay was triggered by the 12 volt wire that normally runs the fuel pump. This relay will then close contact and allow current to the fuel pump from a big beefy wire. You might think why we need a bigger wire for this fuel pump. Well, what we need to do first is we need to explain and understand Ohm's Law, which is the fundamentals of electrical work. Ohm's Law is the relationship between voltage, current and resistance, the three main things with electrical work. I'll show you on the screen now, Ohm's Law triangle. This is how you do your calculations. So we have voltage, current and resistance. Voltage is measured in volts, current is measured in amps and resistance is measured in ohms. Voltage is influenced by the battery or cell or whatever is supplying power to the circuit. In this case, a lead acid battery, which give or take will supply 12 to 14.7 volts. Current is influenced by whatever item is pulling power from the circuit. Every electrical item draws an amount of current. Small things like a bulb for a check engine light on a dashboard might draw 150 milliamps maybe, whereas big large thermofans like the ones on my Patrol may draw 20 amps each, which is quite a lot. Current is also influenced by resistance. Now resistance is influenced by quite a few factors which we need to take into account. The biggest one is wire size. A smaller wire will have a much higher resistance, as the area available for electrons to flow is much smaller cross-sectionally. This means the electrons will rub against each other, causing friction, which in turn causes heat. That's something you need to remember. Higher resistance means more heat. Wire length also has the exact same effect. A longer wire means more length for the electrons to pass through, in turn meaning more resistance. A second factor influencing resistance is heat itself. A hot wire will have its metal atoms vibrating faster, meaning that the flowing electrons will crash into these, rub against these moving atoms, creating more heat. The relationship between heat and resistance is linear if you graph it. If a circuit is too restricted or too much resistance is present, it will cause the voltage to drop. Voltage drop is an indication of how much load the circuit is under. In some cases, the voltage drop will be so severe that you will not be able to turn the device on because the voltage is too low to run it. So if we wanted to calculate what the wire size we would need to fit a 20 amp air compressor 3 meters from the battery, we would do as follows. First, you would measure our running battery voltage, 13.8 in this case. We would then multiply this by 0.95 to get a 5% voltage drop measurement. 5% is give or take an allowable voltage drop for the system to not be under too much load. However, if you want to be safe, you can use 3%. So in this case, it would be 13.8 times 0.97. But if we're using 5% voltage drop for 13.8 volts, that'll give us 13.11 volts. So now what we want to calculate is the resistance. So resistance is equal to V over I for 13.11. This is going to give us 0.65 ohms. So if we chose an 18 gauge wire as estimated for what we would need, we'd use resistance per meter of the wire. If you look online, there's usually charts for resistance per 1,000 meters. So just divide that by 1,000, you'll get the resistance per meter, and then times that by 3. In this case, we're going to get 0.0642. What we're going to do now is add this resistance to the other resistance we got from our air compressor running, giving 0.7142 ohms. Plugging this into V equals IR at 13.8 volts, we are given a current output of 19.32 amps, which is not equal to 20 amps. If we do the same calculation now, but with 12 gauge wire, 12 gauge wire has 0.0159 ohms per 3 meters. I is going to equal 13.8 divided by 0.669. This shows that 12 gauge wire is sufficient for the current supply at 3 meters of length. A slightly quicker way to verify this is to use the full 13.8 volts in R equals V over I at 20 amps. This will give you 0.69 ohms. If we take the 0.65 when we did the same calculation for 5% voltage drop, we can quickly verify by adding the 3 meters worth of resistance of each wire size until we get the given resistance becoming less than 0.69 ohms. This is a long way to do it. There are wire size calculators on the internet, but this is just good basics so you can do it yourself on a calculator. I'll give you a quick demonstration why this is so easy. For our next example, we've got a set of glow plugs, 6 of them. Altogether they're drawing 40 amps and they're a meter away from the battery. So I've dug through the shed and I've found this little coil of wire. It says 25 amps on the front. For us to calculate if this wire will work, we'll do our 5% voltage drop measurement of 13.11 volts. We'll then find the resistance at 13.11 volts for 40 amps, which is 0.33 ohms. The resistance at 13.8 volts would be 0.346 ohms. So the 25 amp wire, it's 2.5 millimeters squared, which is 10 gauge. So 10 gauge wire, according to the chart, is 0.004 ohms a meter. If we plug this together with 0.33 ohms, this equals 0.334 ohms. 13.8 volts then divided by 0.334 gives you 41.34 amps. Therefore, we have confirmed that we can safely use this wire for a 40 amp circuit despite its label saying 25 amps. Its label will say 25 amps because that's the maximum amperage you can run through it at the entire length of the coil. If this has gone over your head, don't really worry. On Google there's plenty of web pages that give you wire size calculations and voltage drop calculations. Even if you're unsure what wire size to go with, there is never a problem to go oversize. If you really wanted, you could use 000 gauge wire and connect that to your dash check engine light. There'd be no problem there. The electrical item is only going to draw as much current as it needs to. I'll show you now with a charged car battery. I'm touching across 2 terminals with a light. You'll see the light goes on. And if I was to connect this straight up to the starter motor of the car, it's going to go ahead and pull 600 amps. So you don't have to worry about it. All it's going to do is supply as much current as it needs. You might look at this and wonder, well, why do you run fuses then? Well, the fuse is what's going to save the wire if you have a bad earth. So let's say you've installed a wire that runs to a switch on the dash. What will happen if the insulation of the wire rubs through and it earths out on the chassis? It's going to try and pull as much current as it can through this wire. If there's no fuse present, the wire's going to pull as much current as it can until it heats up and melts. That's why the fuse is there. The fuse is going to pop when it tries to pull any more current than it needs to at that amperage. Anyway, I think that's enough talking about the wires themselves. What we're going to talk about now is the actual tooling that you're going to need to be able to wire up things successfully. So we'll have a look through the wiring bag that I've always ran with. I've built this over the course of quite a few years. There's quite a few expensive tools in here, or relatively expensive ones. But you don't really need all of them to start off. I'd say to start off, the first thing you'll need is a good wire stripper, just like the one here. All the wire stripper does is allow you to easily pull the ends off the wires, just so you're not messing around with a sharp knife, which can take little bits of the conductive material away and increase the overall resistance of the wire. And then as well as that, what we've got here is a whole box full of connections. So one of my favourite connectors here are these little brass crimp connectors. These allow you to make good solid connections when you're connecting wires together. You can solder wires together with these solder seal ones that I'm pointing to now, but I myself like to crimp them together with the brass connections and then put solder seal over them. When you're soldering the wire, they can move and they can come past each other so that there's not a full solid connection. And it just makes things easier because even when you twist wires together to solder them, they can come apart. So if you crimp them together with the brass connectors, they stay nice and strong. As well as that, you can see I've got all of these spade and bullet connectors. It doesn't really matter which ones of these you use, however do keep in mind that certain sizes of these have certain current ratings, so you'll just have to check them if you're going to be putting a circuit together with them included. Next up in the list is a crimping tool. So this one here was a stupidly expensive tool I bought from over east. This is what I used when I wired up the wiring loom for my Hilux. This tool has the super small anvils in it, which allows you to swage and pin the connectors for all of the really small sensors in the engine bay. These sensor wires are usually very small and much smaller than anything that will run a spade or a bullet connector. I do highly recommend getting a tool like this. It makes jobs super easy. There is another crimping tool in here. This I've found is nicer for bigger wires. It gets a little bit more mechanical advantage and it means you don't have to squeeze it as hard with 2 hands when you're putting a connection on. And then as well as that, there's this tool here for much larger connections. I barely use this tool. This is for massive, big, high amperage connections. I may use this 1 or 2 times when I'm doing battery relocations and doing big connections for things like winches. Again, it is an expensive tool and I don't suggest buying one if you're not going to use it very often, as it's sort of a waste of money. If people are interested, I can go into a much more in-depth video for making the wiring connections. However, most of this is very self-explanatory. I'll put together one wire here with a brass connector. So you just have to strip the ends off 2 wires and then you can crimp them together. You've just got to be careful to slide your insulation over the wire before you strip it, because that makes things much easier. Spade connectors are the same, you just crimp them together and they allow you to do and undo the connection if you need to get things off. I'm not going to worry about solder seal. I've used it before and you can find videos of how to use it on YouTube. It's pretty easy. Ideally you use a heat gun when you put it together, but you can use a cigarette lighter if you're going MacGyver style. I have blown up a cigarette lighter in my hand, so be careful when you do things. But yeah, just keep that in mind. It's great stuff to have and it makes a really good connection. So at the very end of the video, you can skip there if you want, I'm going to put all of the calculations that we do here in order and the reasoning behind them. So you'll be able to screenshot that and keep it on your phone or keep it on your computer just to have around, which is good. Hopefully it'll help you on a rainy day. Okay, I think that wraps everything up in this video that I wanted to cover. I realise this is a much more broader topic than I would have liked for a simple introduction video. However, I've covered as much as I wanted to, and hopefully enough for people to understand to a point where they're able to do their own wiring now. As always, if you have any questions about the video, drop a comment, or you can message me directly on Instagram. I'm progressing slowly with the BMW, there'll be a video about that soon. I'm going to make an update video on the Holset Turbo because there's been some interest in that. So I'll keep videos coming. Again, I hope everyone had a very good Christmas break and a happy new year, and I'll talk to you all later.